Okay, let's continue with this nice stick. I'm not a fan of high tech. Okay, we have been explaining how to find adjacencies and how to find V-structures. We don't have time for all the details, but I should skip maybe some of the rules. So the idea is the following. If you found the corresponding undirected graph, then you can orient some edges just of the basis of this finding V structures. And then a lot of edges still remain undirected. And then you recall that the assumption was that you want to get an acyclic graph, and the further assumption is that you already found all the V structures. So you can orient some edges based on the assumption that no cycles should occur and no additional V structures should occur. And instead of going through all the rules, I would start with an example taken from Spert's. So this is the true DAG. Then we start with a fully undirected graph, fully connected. And we first remove all edges for variables that are independent given the empty set. Okay, we end up with this graph because we have identified x1. This is a typo. We remove the edge xw and yw, and then we remove all edges for variables that become independent if I condition on one variable, and I end up with this undirected graph, which is already the skeleton. By conditioning on subsets of size 2, you can then realize that no further edges should be removed. That means that you already stop with subset size 1. Okay, then you identify this V structure. What's the idea? You first observe that you have a triple where those two variables are unconnected, and then you check that the set that makes them conditionally independent does not contain the variable z, and therefore we have a V structure. So we have this separating set SYW, but it does not contain z, so it can only be a collider. Then we necessarily need to orient this edge this way, otherwise we would create an additional V structure here and an additional V structure here. And then this edge remains undirected, so it really could be both ways because this is a Markov equivalence class. So we get an output where only some of the edges are directed and some undirected. So that's the final output of the algorithm. Okay, we haven't been talking about one important problem. How do you do this conditional independence test? So most algorithms, if you look in the books of Spertus and Pearl and so on, then they are just talking as if we would have perfect independence testing. But what they do in the algorithms that are online is, for the discrete case, they just use contingency tables. It's like classical statisticians. For the multivariate case, for the continuous case, they assume multivariate Gaussian variables. And then all conditional independences can be read from the covariance matrix. So this is, of course, a very strong assumption. For non-Gaussian continuous variables, it's quite challenging to invent conditional independence tests. Bernhard will talk a bit about that, how to use kernel methods for this enterprise. There are important improvements for this causal inference methods. First of all, there is something called conservative PC. It depends on a weaker form of faithfulness. Because if you recall how faithfulness enters into the algorithms, then you can easily imagine that it's not really robust. So you orient a lot of edges, and then you orient further edges based on the assumption that you don't want to create cycles. So you can easily have further errors if you have been some wrong orientations in the first place. Okay, and so this algorithm uses weaker form of faithfulness and is therefore more robust. Then there is an algorithm that works in the presence of latent common causes. Several people already asked for that in the break. Actually, if you include common causes, then it first seems like an infinite problem because the set of possible common causes could be infinite. But people have been showing that for every model with general latent common causes, there is always a latent model where a latent variable influences only two observed ones. And this is an important restriction, because then the set of possible models becomes finite, and you can still do a finite search over the set of possible causal structures. And you can really obtain causal statements also in this case. There's a homepage that I should mention, because these people at Carnegie Mellon have been doing this since '93 at least. So you can find implementations for these algorithms. I think someone asked about score-based methods and Bayesian approaches. You can also take the Bayesian viewpoint and say, well, I define a prior over the set of possible DAGs. Then, given each DAG, these conditionals are free parameters. So I define priors on the set of parameters, and I compute a posterior probability for the DAG. And one can show that this implicitly also prefers faithful DAGs. I don't want to talk about that, but that was not non-Bayesian ideology. I'm quite agnostic about that. Okay, so one important point for us is that whether Markov equivalent DAGs obtain the same posterior probability heavily depends on the prior. And designing good priors is hard. And people have been working with priors for which Markov equivalent DAGs always get the same posterior probability. I remember a discussion many years ago where we started our causal inference. Someone who said, well, we need a prior where Markov equivalent DAGs get the same posterior. And I asked why? Well, because they are indistinguishable. And I found this argument silly. And I mean, actually, we want to distinguish equivalent DAGs, and therefore we need reasonable priors. And we will later show, I mean, we will not explicitly define the priors, but we will show prior assumptions that make them identifiable. People ask me about applications, but I should skip that. So I just for time constraints. But in 2007, there was a very interesting and impressive application of these methods in the context of biology. And I remember talks that I gave before that time, and people asked me always about relevant applications, and it was always hard to answer. But I think in the meantime, there's already some nice examples around. Okay, but Bernhard mentioned the equivalent Markov conditions, and that I'm going to explain why they are equivalent, at least give some first sketch. We had the following conditions. We have the existence of the functional causal model, so these structural equation models. We have the local causal Markov condition saying that every variable is statistically independent of non-descendants given the parents. And we have the global causal Markov condition saying that deseparated variables are conditionally independent. And we have this factorization into the conditionals given the direct causes. And to give you an idea why they are equivalent, first, the step from local Markov condition to the factorization. We start with a terminal node xn, so a node that has no effects. Then the set of non-descendants is just the set of all remaining variables. So xn would be conditionally independent of all remaining variables given its parents. Hence, the general decomposition of this joint distribution into the joint distribution of the remaining n-1 variables and this conditional simplifies into this expression, because the replacement of this expression into that one is exactly the definition of conditional independence. And then, so you have replaced this conditional by a simpler one, and doing this with the other variables. So formally it's an induction over n yields the desired formula. Okay. Then we have the fact that factorization implies the global Markov condition. That's the most difficult step that I want to skip. I just want to mention that it uses already known results from undirected graphs. So there's this red book of Lauritsen with graphical models where you find a lot of material about undirected graphs. Okay, global Markov condition implies local Markov condition is kind of trivial. So trivial in the sense that this is really the complete proof. Yeah, actually, global Markov condition says deseparation implies independence. So you just have to show that the variables we are talking about in the local Markov condition are deseparated. Okay, functional model or structural equation model, it's the same, implies local Markov condition. This is also quite easy to understand the idea. If you recall that, so this is the original DAG, and then you recall that the functional equation model, the structural equation model, adds a noise variable to every observed variable. And then you recall that every variable is a deterministic function from its parents in this augmented graph. Then you can see that if you assume that the unexplained noise terms are jointly independent, and then they are unconditionally independent of their non-descendants. So for these variables, you have already checked the local Markov condition. For the observed variables, you can also easily check the local Markov condition. And then we already know that the local Markov condition implies the global Markov condition, because this was the difficult step that I skipped. And then the global Markov condition in G prime implies the local Markov condition in G, because you just need to check by hand that d-separation in G prime implies the conditional independence that you want in the DAG G. I think there's nothing sophisticated about that. Now there's one step missing, the fact that the factorization implies the existence of the functional model. So we are supposed to generate these conditionals in the factorization by a deterministic function and some noise term. And there's a very, very simple way to define that function. I think it's the easiest way is to explain it for the finite case, but for the discrete case, but the continuous one follows the same way. So we define a vector-valued noise variable where each component corresponds to a possible value of the parents. So of course, if you have many parents, then this is a lot of components, but never mind. Then the structural equation just reads, evaluate the corresponding component. So the only influence, so you have a lot of noise terms, vector-valued noise term, and the parents just tell you which component to look at. And then you assume that each component of the noise is distributed according to this conditional that you want. And then it's easy to see that this already generates this conditional. You can look at these structural equation models also from a different point of view. And consider the noise variable as function valued. So the set of possible noise values is the set of possible functions from x to y. So this noise just chooses a possible function. And so this u, so to speak, chooses a mechanism that connects x and y. To give you a simple example, if x and y are binary, then the set of possible functions are the identity, not the always one function or always zero. And assume, for instance, you observe that there are no dependencies between x and y, and both are uniformly distributed. Then you can either, no, I think you don't need the uniform distribution. You can, to generate independent random variables, you can either assign probability 1/2 to the constant function 0 and probability 1/2 to the constant function 1. Or you can have a random switching between the identity and not, both with probability 1/2. So both induce the uniform distribution for y independent of x. This example shows that the structural equation models determine the conditional distributions and the joint distribution, but not vice versa. So to induce the same joint distribution, you may have different structural equations. This is where the break was. This is our personal break to swap speakers.
So let's briefly recap. So this was sort of the general theory, tutorial material, and now we talk about mostly about stuff that we have done in Tübingen. and how this connects to what you've learned about so far. So you will notice that we have already gradually prepared things, maybe moving away a little bit from this conditional independence based method towards machine learning point of view, where you think more about what kind of assumptions do you need to make on functions in order to make this problem solvable. So let me pick up from there and briefly recap what we have. So we have these functional models. Each variable is a function of its parent and noise. The noises are jointly independent. We know that this entails a certain joint density with a particular conditional independence structure, and all these methods are exploiting these properties or this conditional independence structure. And we know that under certain assumptions, faithfulness, etc., we can, given P, recover an equivalence class containing the correct graph using conditional independence testing. Now, one problem of this is that this does not work at all for graphs with only two vertices, because if we have only two variables, there's nothing to condition on. So we cannot make a non-trivial conditional statement because it would involve three variables. So the Markov equivalence class will just contain both possible graphs, no matter what causes what, if we assume that there is a causal link between two vertices. So that's a pretty basic problem. And it's kind of, I mean, people know that without, just in this framework, as we have discussed it so far, this is a problem that cannot be solved. Even though, from a certain point of view, one should think that the two variable case should be the easiest one. So that's a problem, and that's the problem that we started with when we started looking at causal inference some years ago. This is a problem even if we have infinite amount of data, because we always have assumed that we know the joint distribution. So that's bad. And things get even worse is if we don't have infinite data, because in that case, actually, conditional independence testing can get arbitrarily hard. And from the machine learning point of view, one should think that possibly both problems can be resolved by making assumptions on the function class. And in a sense, that's been our working hypothesis, and still our hypothesis. And we'll show you what kind of progress we made in this direction. Okay, so let's talk about this two variable case. So we have two observables. What can we do? And maybe first to motivate that this is an important problem. So this is another philosopher here, Nietzsche, who wrote this book here. I think within a week he must have been in some kind of writing frenzy, and in this book he writes about the 4 great errors of human reason or something like that, and he says the first of these 4 great errors is the error of mistaking cause for consequence. So he says there's no more dangerous error, and he calls it reason's intrinsic form of corruption. So let's look at this problem. So we have this structural equation model with only 2 variables. So what does it mean? Let's consider the non-trivial case where there is a link between the variables, but we don't know which way around it goes. We know that each variable has their noise variable that influences them. But actually, we can kind of ignore this noise variable here, because x is just a function of the noise variable. So let's, rather than having a noise variable and then x be a deterministic function of it, we can just say x is a random variable itself, which means we have actually the complete description of our situation by looking at these 3 variables. The noise variables are jointly independent, which now means x and n are independent. And in this case, of course, it's just pairwise dependence, pairwise independence. We only have 2 variables. So that's the general situation in the 2 variable case. And I told you it's impossible to infer this direction. And that holds true if we assume that there's this general functional model where y is a function of x and noise. So if we have no further assumption, then it might we cannot distinguish this situation from the situation where x is some other function of y and some other noise. And Dominik already told you a little bit why this noise has such a strong influence on these structural equation models. It essentially chooses the function. So for instance, a special case of what Dominik just said would be if the noise were a discrete random variable that can take values between 1 and d or between d different states. then this noise could simply switch between the different mechanisms. So, and this could be completely different, like knots and identity, whatever. So completely different mechanisms, and somehow intuitively it seems to be clear that in such a situation, and in practice, of course, the noise could take more than just the different values. It could be a continuous variable. In such a situation, if we make no assumptions on how this function here of two variables depends on the noise, this can be arbitrarily complicated, and there's just no hope of learning this kind of model from data, from a finite data set. So we have to make an assumption that in some sense this function depends on the noise in a simple way, and the simplest such assumption is probably that the noise is additive. So that's our major assumption for the next 10 minutes. And one can think about how to justify it in various ways. Maybe the easiest, if one doesn't want to spend too much time on it, the easiest would be to say, well, if the function is reasonably smooth, and maybe if this variable is reasonably concentrated, then this is like a first order linearization of how the function depends on this noise variable. We just take the linear term. Okay, so that's our assumption, but it is a significant assumption, and we need it, otherwise the problem doesn't get solvable. And then we were thinking about this problem about 5 years ago, and we pretty quickly we got the intuition why it makes the problem identifiable, but then it took a while to prove it. And the intuition is as follows. So again, let me remind you, the model is, things look like that. That's the forward model, and now our question is, can we fit a backward model of the same form? So given some joint distribution of x and y, is it the case that we can fit both directions, or might it be the case that the problem now is suddenly asymmetric, and if the data truly was generated by such a model, then a backward model would not fit? So that's the model. So let's assume, for a simple example, that the function is nonlinear, and let's assume that this noise here has some bounded range. Then we can think of it like this. We have our nonlinear function, and then this additive noise of bounded range is added to it. So we have this kind of slab around the function that has the same diameter when measured like this everywhere. And now the question is, if we think of things backwards, can we write it the same way? And it turns out, if you now think of y as the input, and then you wanted to add some noise in that direction, then somehow this noise would have to vary. So it would be no longer independent of y. It would be maybe larger in some places, some areas of this axis, and would be smaller in some other areas, so it would depend on it. And that would be a problem. So intuitively, it seems to be plausible that this is no longer a symmetric situation. And one can prove that. And we will not prove it, but just to give you an idea. So what does this theorem say? Theorem says, let's assume there is such a model in the forward direction. So it's a joint density. And the model is, it factorizes between a density over the input and density of the noise, and the noise is additive. So this is just the density of y minus the function, right? This is just the noise. So product of density of noise, density of input. And let's now assume if there's in addition a backward model of the same form. So suppose we can write it in both directions this way. So that's exactly the same thing, just in the backward direction. Then it turns out, under certain generic conditions, we can derive a differential equation that couples all these things together in a specific way. And the differential equation will depend both on the log of the noise density and the log of the input density, and on the function. So this nonlinear function that mediates between input and output. And it's this complicated looking thing which we don't analyze now, but the main message is that generically this differential equation has a three-dimensional solution space. So for instance, if you specify the density of the input and the density of the noise, then it's very unlikely that from this possibly infinite dimensional function space, we'd have to, if we don't have a restriction on this one-dimensional function f, So from this infinite dimensional function space, it turns out there's just a very small space from which you could take the function such that this and this can simultaneously be satisfied, or that such that this differential equation, which is the implication of this, can be satisfied. So the message is it's very unlikely that a function and these noise distributions are such that this model becomes non-identifiable. So in the generic case, this is identifiable, which means we can determine which way around the error goes. And that's nice. And actually also the cases where we can't do it make sense. So it's, for instance, the case when the functions is linear and the noise is Gaussian. So it was known before that the problem is solvable for linear functions and non-Gaussian noises. It's related to independent component analysis. What was not known, and what's nice about this, is that it turns out when the functions get non-linear, then we can even deal with Gaussian noise. So in this sense, there's an advantage here to having nonlinear functions. It makes the problem, in some sense easier. Okay, so. Well, it just if you want to ask whether something is Gaussian, it's nice if you talk about the logarithm of the density, because then it just becomes a quadratic function, and then these conditions with the third derivative being 0 suddenly are quite nice. Yeah. 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 Okay. So the question is it more difficult to identify the causal direction if the function is linear? So the answer would be, if the noise is Gaussian, then it's more difficult for linear functions because it's impossible. If the noise is non-Gaussian, then I don't know what I should say. Hard to say, yeah. In a sense, maybe the nonlinearity still adds some information. Yeah. So yeah, it could be that it's still easier. So in the proof, okay, I'm not showing the proof anyway, so maybe I shouldn't talk about this one in detail. So there's a very briefly alternative or an interesting interpretation, which also comes somehow from this ICA field in terms of entropies in mutual information, which actually I'm going to skip. So if you're interested in ICA, etc., look at this slide. They will be on the web. So because last time we gave this tutorial, we had to skip some of the very last material, and we really want to show some of this because, yeah, you'll see here. Okay, so then how do we construct a method from this, an inference method? Well, it's kind of intuitively clear. So we will try to fit additive noise models in the forward direction and in the backward direction. And we just see in which direction it fits better, or in which direction the noises become independent. So we do a nonlinear regression. We compute the residual error, and then we check whether the error and the input, so in this case we consider X the input, are statistically independent. Yeah. So for instance, there's this data set, which is from the German Weather Service, the average temperature of places in Germany and the altitude where these temperatures are measured. You can see the highest place in Germany is 3,000. Huh? You mentioned it, yeah. Yeah. Did you already talk about the independent? No. No. Okay, so the highest place, 3,000 meters. You see the temperature is goes down as you go higher, as what we expect, and we have an understanding why this is the case. There are some physical reasons why places get colder as you go higher. So the causal direction, we believe, is that the altitude causes the temperature. If you change the altitude of a place somehow, maybe you could imagine a hypothetical intervention, then you would expect that the temperature goes down. But if you just change the temperature by putting a lot of heating, so I don't know how you would do it, you wouldn't expect that somehow the ground goes up or down. So of course, these cases you can always discuss, and there might be confounders even in such situations. But roughly speaking, it seems to be reasonable to have the causality this way around. And lo and behold, it turns out that the residuals are quite independent in this direction, and in the backward direction they would be quite independent here, in the backward direction quite dependent. So we would, in this case, decide altitude causes temperature. And just briefly, there's a number of generalizations. One can include a post-nonlinearity, which means one can have a nonlinear function around here, or equivalently over here, which kind of makes sense because a fixed function doesn't change dependence properties. You can do that. You can also generalize to graphs with more than two vertices. So if you're willing to make such an assumption that makes the two-variable case identifiable, then you can exploit this also for bigger graphs. So if, for instance, if you know that, if you're willing to assume that the noise is additive in your graphical model, so you assume your graphical model comes from an underlying functional model with additive noise, turns out then the graph learning becomes easier. There's some initial work on graphs with loops as well. Okay, so so far I just said we do a regression forward, we check whether the noises are independent, we do the same backward and compare. In some sense that's a little bit silly because regression, so if you do regression you have to regularize or do something. I mean, if you perfectly interpolate the data, your errors will be zero, in which case it doesn't make sense to test for independence of noises. So you will have to make sure that your noises are not zero by regularizing. You have some trade-off between fitting the data and the model complexity. But then if you exaggerate that, if you regularize too strongly, then your noise suddenly might look dependent just by this, in a sense, by this confounding from the regularizer. So normal regression might not be the best method to do this, and we did some work on developing a regression method that doesn't minimize squared error, for instance, but that minimizes dependence of the residuals. So that only that's of course a more complicated regression method. You will have to do some statistical or some independence. You need some independence measure that you minimize. But it's closer to doing the right thing because you really want an explanation where the noises are independent. You don't really, from the causal point of view, you don't care about whether the mean-squared error is small. So one can do this, and this is using some of these Hilbert's kernel methods to measure dependencies. And I will just very briefly mention a little bit of these methods, but not a lot. So the basic idea is that you use something that's called the kernel mean map. Kernel mean map goes as follows. You take your mapping into the reproducing kernel Hilbert space that I told you about yesterday. So this is one way to write it. A point x gets mapped into a kernel centered on x, so that's a function in the reproducing kernel Hilbert space. And now, rather than just mapping one point, I'm going to map a whole probability measure as follows. I will, in a sense, sort of sample infinitely many points from that measure, map each of them, and then take the average. So formally that means I'm looking at this map and taking the expectation with respect to sampling points from the probability measure. So that means that's an embedding of a probability measure in a reproducing kernel Hilbert space. We have to make a few mild assumptions on the kernel to make sure that this expectation is finite. If that's the case, that's why I didn't put them on this slide here, then this is well defined. And the nice thing about this mapping now is we can prove that if the kernel satisfies a certain condition, which is called universality, or there's a related condition called, there's a characteristic kernel, which I don't go into detail on, but I just want to say that, for instance, the Gaussian satisfies this condition. If that's the case, then this is an injective mapping. So we don't, injective means we can invert this, so we don't lose any information. So it's really quite impressive. So if we take two probability measures, if they map to the same point in the reproducing kernel space, they are actually identical. So even though this is in some sense only one point, of course in a higher dimensional space, this point remembers all the information that went into it. Okay, so that's nice because so now we can embed probability measures in this space without loss of information, and we are now in a linear space. We can with a dot product, we can do all sorts of nice things in there, and for instance, we can formulate statistical independence measures and tests like this. Okay, and the way we are going to do is we represent. We map both a joint, so if we are interested in independence between x and y or in a dependence measure, we're going to take the joint distribution of x and y, map it into this space, and then we will take the product of the marginals, also map it in that space. By the injectivity of this mapping, these two distributions will map to the same point if and only if they are equal. And testing whether they're equal is exactly independence testing. Okay, so I'm going to skip this. So there's this, this leads to this quantity that people have called the Hilbert-Schmidt independence criterion. It can also be written as the norm of a certain Hilbert-Schmidt operator. And so here I told you the idea. We embed the joint, we embed the product of the marginals. And yeah, one can write down empirical estimators that involve kernel matrices. So we have one kernel on the x's, one kernel on the y's. And then we will get something like this, the product of the two kernel matrices, or actually there's some issue of centering. If we do that, then we have two more matrices, but essentially we just have a product of some matrices. We take the trace of this, and it turns out this quantity actually is an empirical estimator of this distance. And then we will have to test whether this distance is somehow significantly different from zero or not. So there's a number of issues about his testing, but maybe I shouldn't go into details on this. Maybe I just briefly mention there's also a normalized version of this Hilbert-Schmidt independence criterion, the HSIC normalized independence, so Hilbert-Schmidt normalized independence criterion, which has a particular nice property that it can be shown to be equal to the mean squared contingency. So this is now this criterion defined in the population sense, so defined in terms of really expectations. So if this mapping is really taking the expectation with respect to the probability measure, so of course for the finite sample case you will not exactly have this, but this statement says that in the population case, actually, this quantity will be equal to the so-called mean squared contingency, which is nice, because the mean squared contingency is this measure of how much a given joint density deviates from the factorizing density, averaged over the joint density. And it turns out that this statement, what I just said, this equality to the HSIC is independent of which kernel we are using for the embedding, as long as it's a universal kernel. So that's nice. One can also show a certain relationship to the mutual information. No more details on this. And I also want to make this one relatively brief. I just want to sort of tell you what is the problem if we... So now we have this measure. Where is it? So if we do this thing based on empirical data, so we don't compute an expectation of points mapped into the feature space, but we compute an average. We have a set of points, we map them all in the feature space, we compute an average. Then we get this empirical quantity that now depends only on the training data, on these kernel matrices containing the training data. Now we want to, let's say we get a certain number, let's say the difference between these two quantities is 2. What are you going to do with this? Does it tell you anything? So what you have to do is then you have to study how you have to come up with what's called a null hypothesis. So for instance, the null hypothesis could be that x and y are independent. So therefore, this quantity here will be 0, the population quantity, but you have only finitely many data points. So how can you tell if you measure 2, is that still 0 or is it not? So you have to think about how this quantity, or our test statistics, this quantity is distributed under the null hypothesis. So you have to imagine, what if truly x and y were independent? What kind of values would I typically expect to measure from this quantity? Just because the quantity is an empirical quantity, it will have some fluctuations. So what if the true value is 0, but nevertheless I only have finitely many data points? What will I expect? And then you can compute or simulate or somehow get a handle on what's called the null distribution. So what values will this typically have? And then you can compare the actually measured value that you get to this null distribution. You can check, are you very much in the tails? Are you like in the 5% that are furthest away, or maybe even 1%? That will give you a significance level for the test. So these are like the main ideas of the problem, what's behind why one has to worry about statistical testing. So we don't do this now, but I just want to say this has to be done, and there's some nice results about this. How to get an expression for the null distribution of this quantity. And there's also some ways how to do it with permutations. So for instance, one can, if given data from the joint distribution, so data pairs x, y, it's actually easy to generate data from the factorizing distribution. How do we do this? Well, we simply apply a permutation to the, for instance, to the y values. So if we mix up all the y's, but we keep the x's, so we pair up the y's with the wrong x's in a sense, then of course the marginal distributions of p of x and p of y don't change, right? We have only changed the ordering of the y's. But we have broken the dependence between the two. So now x and y are independent. So this is like a sample from a factorizing distribution. And the case, maybe this kind of view makes it clear that the case of conditional independence is significantly harder, because now you would have to generate, so now the problem is given these triples, so each observation is a triple from the joint distribution of p, x, and y. Now we wanted, if we wanted to do a trick like this, we would need to generate samples that are consistent with this, sort of from a distribution where this conditional independence property holds true. But we want to do this without changing, so previously we wanted to do it without changing the marginals. This time we want to do it without changing these conditionals, because the question of conditional independence is the question of whether we can factorize into a product of these two. So that's harder. One way to do it is if z only takes very few values, then we could just permute within the groups, and that would satisfy this thing. But of course, if z is a continuous variable, which is something that has been very rarely considered in the causal inference community, probably for this reason. If it's binary, of course, that's relatively easy. If you have one binary variable that you condition on that's small, that's in a sense twice as hard as an unconditional test. But if you have a continuous z, it takes infinitely many values. What are you going to do? Will you cluster them or something like that? And especially if it's in a multidimensional space, so you have multiple variables or vectorial variables that you condition on, it can get arbitrarily complicated. Okay, so I think I'm going to skip this. I just want to briefly say, what is this about? So I said before, if we are willing to make an assumption of additive noise, we can solve the two-variable problem. And this is some work about the problem where, a bit closer to the Reichenbach setting, we observe two variables that are dependent. And now we want to know, does x cause y, does y cause x, or is there a confounder that causes both of them? And it turns out if we're willing to make assumptions that the way the confounder causes both of them is again with additive noise, then one can prove something about this, and one can come up with an algorithm which essentially does something like dimensionality reduction, but requiring that the errors are independent. So it's like a dimensionality reduction method that doesn't care about mean squared error or something like this, but only about independence of errors. Okay, and in this context, I also should say that Eleni Skorica, some of you might know her, she's here, a PhD student, has done some very interesting work on identifying discrete confounders, and it's a little bit related to this last method. In this case, is not dimensionality reduction, but it's a kind of an independence-based clustering method. And she presented this at AI Stats this year, and I think she had a poster about this. Or if you haven't seen the poster, just talk to her. Or what did I say? Yeah. Oh, sorry, UAI this year. Yeah. So that's just last month. Okay. So far we have done the inference. We solved the two-variable problem in some cases, making the assumption of independence of noise. So we are looking at properties of noise. What about if there is no noise? So the functional dependency doesn't have any noise added. So whatever we did so far then shouldn't work. And it turns out one can also handle that case by making a different kind of assumption that's very interesting that we're trying to exploit in these kind of problems. And that's an assumption of independence of input and mechanism. So the graph is like this again. Remember, we can identify the cause and its noise variable. And then we have some function, here is written like phi, that computes the effect variable depending on the value of the cause variable and the noise that affects the effect variable. And this function we think of as the mechanism, or sometimes we think of this function as the mechanism, sometimes we think of the conditional of E given C, the mechanism. So the conditional sort of contains the function and the noise. But the assumption that we want to make, and now this is fairly informal first, is that the distribution of the cause and the distribution of the and the conditional, so the mechanism, are in some sense independent. So the mechanism, we think of it as a physical process in the world, and this process somehow doesn't care what kind of input distributions it is faced with. So what you feed into it doesn't affect the mechanism in this case. And that's an assumption, so it could be violated. It's not vacuous, because how could it be violated? It could be, for instance, that there are mechanisms out there in the world that have been tuned, for instance, by evolution to expect certain input distributions. In that case, the violence would be broken. The assumption would be violated. If I'm trying to speak fast, then these kind of things happen. Okay, so but we're willing to make this assumption, and we believe that in many cases it's reasonable. So if there are physical systems generating causality, it's a reasonable assumption to consider. And then let's look at this deterministic setting, where we have an input distribution. We have a mechanism, and for simplicity, the mechanism is just a function. There's no noise. We are assuming that intuitively this mechanism doesn't care about what distribution we feed in. That's our independence. And then the crucial observation is that under this assumption, if this function is non-trivial, if it's non-linear, we should be able to find some traces of what this function did on the output distribution. So you all know that this function will transform this density to produce some density over the outputs. So when I say there's no noise, I mean there's no additive noise or no sort of noise that comes from outside here. But of course, the x itself is a random variable here. But if this function is non-trivial, so where this function is flat, then all this mass of the density in this area, in this flat area, is concentrated in this relatively small interval of y's, just because the function is flat here intuitively. So if you imagine you sample points from this distribution, you propagate them through the functions, a lot of them will end up in this area just because the function is flat. So that's how densities transform according to the derivative of this function and or of the inverse function. And then we get this output density which is large wherever this function was flat or where the inverse was steep. So that's the intuition, and one can formalize this as follows. So let's, for simplicity, assume that the function is monotonously increasing and it's a bijection of the unit interval. What we're going to do, and if you've got this intuition and if you're maybe not too much into mathematics, then you don't have to pay attention to this slide. But for the mathematicians, formally what you can do is you can view the value of the density as a random variable. So now we're going to introduce a probability space, which is just a 0-1 interval with respect to Lebesgue measure. So we will randomly draw points between 0 and 1. And then we will look at what value does the density have here, and we will consider that a random variable. And also we will look at what value does log f prime have at this point. That's also going to be a random variable, right? It's just a particular kind of random experiment. We draw points between 0 and 1, evaluate these two functions. Density is just a function. This gives us random variables. And now we will postulate that these two random variables should have zero covariance. So you might argue maybe that's not all. Maybe we should be postulating more than just this kind of covariance between two particular functions, one of them non-linearly transformed. But I guess you will agree that if mechanism and input are independent, we would expect that like this covariance should be zero. It should average out to zero somehow. And the nice thing about this postulate now is that if we are willing to postulate this, then we can prove that it's violated in the backward direction. In the following sense, in the backward direction, we have this inequality, so f to the minus 1 and py. And equality only holds true if the function is the identity. Of course, if the function is the identity, there's not going to be anything we can distinguish between forward and backward. If the function is not the identity, then in the backward direction, this quantity will be strictly positive. So we have an asymmetry. And this asymmetry can be also expressed equivalently in various other forms and related to notions of information geometry. And maybe I should not talk much about this. So this postulate here, well, maybe just one of them, implies the following statement for the Kullback-Leibler divergences or relative entropies. It implies the statement that, so again, you try to remember this picture or put it into your iconic memory for a second. So we have input distribution, output distribution, we have the function. Now the statement is the output distribution. It will typically deviate from the uniform of the output, so U is always a uniform one. How much does it deviate from a uniform one? So how regular is the output distribution? And the statement is this irregularity is a sum of two terms. One of them is the irregularity of the input distribution, and one is the irregularity that we would see on the output if we were to start, So this Vy is the output that we would get if we started with uniform inputs. So suppose this thought experiment, we put in uniform input, just by the fact that the function is irregular, we already get a non-uniform output. This measures the irregularity generated by the function. This measures the irregularity that's already in Px. And the non-trivial statement is that this is just a sum. So these two things add up to generate this. There's nothing canceling each other. That's correct in the forward direction. Okay, so one can come up with practical estimators that sort of try to check essentially things that are related to this, or check the covariance between this kind of quantities. And this is somehow related to the slope, and we have a logarithm here, so I think you can imagine what it's about. And then we have a practical method, and we applied it to a number of data sets. And we applied not just this method, but also the one that I talked about previously. And we have this set of 80 cause-effect pairs that we've collected and labeled ourselves according to what's the ground truth. And then the results look as follows. So just very briefly, first of all, typically these methods, they take decisions based on some real numbers. So you have some forward value for the dependence measure and some backward value, or maybe you have a p-value in forward and backward direction. And if these two numbers are very similar, you might not want to decide, is it forward or backward? So let's give them the chance to reject the decision. This is decision rate, so if we always force them to decide, we're over here, but if we're telling them, look, try to be conservative, don't decide if these two numbers are similar, we move over here, and you see, generally speaking, the methods, some methods tend to get better if you don't force them to decide. there's this gray area, which is the area where you would expect the results to be if your algorithm were just random guessing. In 95% of the cases, you would end up in this gray area. So we are, let's consider everything outside of this gray area significant. Then you can see that this additive noise model that I talked about before can get significant results. I mean, it's certainly overall the behavior of the curve is such that you wouldn't say this is like a typical sample from the gray area. And it can get actually pretty good results if you're willing to not force it to decide all the time. And this information geometric method also can sometimes have pretty good results. It's not completely clear why it behaves like this. It's also not clear whether, when we're applying this to noisy data sets, and it's really making an assumption of no noise, so it's all a little bit, one should take it with a grain of salt, but the overall message is one can do this better than chance, and which people thought of difficult or impossible before. So what is it good for? Suppose we can decide about cause and effect. Does it have any bearing for machine learning? Or is it just a curiosity? So for instance, once we submitted a paper to ICML about deciding about the direction of time series. So can we tell whether a time series is forward or backward? And some of the reviewers said this is a completely stupid question. They thought this is, why would anyone be interested in whether time series is forward or backwards? And but I think we were lucky, and the area chair decided it's interesting and just accepted it anyway. But here's maybe another motivation why machine learning people should be interested in this. And it turns out that the causal direction has some implications for common machine learning scenarios. And first of all, I want to point out that we don't always, we usually don't care about what is the causal direction, but we sometimes make predictions aligned with the causal direction. So for instance, in this bioinformatics problem, predicting genes from mRNA, there is a physical or biological mechanism that takes mRNA as input and then controlled by various other things, eventually produces genes. So that's a causal mechanism. And if we predict genes from mRNA, we are predicting in the same direction as the causal mechanism. On the other hand, many problems, if not the majority of classification problems at least, are anti-causal in the sense that the prediction is in the opposite direction. So here, for instance, these digits were generated by someone in their head thinking, I want to produce a digit 3, and then generating the image. So in that sense, the class label is the cause and the image is the effect, and we're trying to go from the effect to the cause. So that's the opposite. And if we now think about, we try to categorize different problems or different settings and what kind of implications we get if we are now still willing to make this assumption that the input distribution and the mechanism are independent. So this assumption is now interesting if we think about how does this assumption read depending on whether X and E are, C and E are X and Y or Y and X, so whether we're forward or backwards. And I just want to point out this one case of semi-supervised learning. So if we are learning in the causal direction, then our assumption simply says that P of X and P of Y given X are independent, right? So in this case, if P of X and P of Y given X are independent in some sense that one should formalize, that means P of X doesn't contain any information about P of Y given X. So if someone gives you additional data from P of X, that's semi-supervised learning, you might get a better estimate of P of X, but it's not going to help you get a better estimate of P of Y given X. And of course, in the end, in machine learning, for instance, if you do regression is defined as estimating the expectation of P of Y given X. So you won't be able to do regression better. So from that point of view, semi-supervised learning should be impossible in the causal direction. Other things like covariate shift should be relatively easy in the causal direction. And in the anti-causal setting, it's the other way around. Covariate shift should be relatively hard. At least should be hard to do it just by things like re-rating. But semi-supervised learning should be possible because if it's true what I said before in a particular formalization, I said that if we're willing to make this independence assumption forward, then it will be violated in the backward direction. So let's assume it's violated. That means, now in this case, that P of X does contain information about P of Y given X. That's great, because then with additional data of P of X, we should be able to construct methods to get more information about P of y given x. And actually, the assumptions that people have come up with to justify semi-supervised learning are exactly about this kind of connections between P of x, P of y given x, only that people don't think of it from the causal point of view. So for instance, the so-called cluster assumption says that points that lie in the same, so it sort of assumes that the density of the inputs is somehow clustered. And the assumption says now, if we find that 2 points lie in the same cluster, then they should have the same label. So that means somehow that P of y given x should be constant, or should at least be on the same side of 0.5 if you're doing classification while you're in a cluster of P of x. So it's a certain kind of connection between the two. And there are other kinds of assumptions justifying semi-supervised learning, and they all can be interpreted as links between these two objects. So that was the idea, and then we wanted to test whether it's true, and we wanted to be lazy. We didn't want to run experiments ourselves. So what we did is we looked for other benchmarks in semi-supervised learning. But before analyzing the data, we always looked at the data sets first and the descriptions. And for each data set, we try to decide, is it a causal problem, or is it an anti-causal problem? Or is it maybe a confounded problem, in which case, in principle, the information to do semi-supervised learning should be there. So in a sense, confounded goes in the same category as anti-causal. But the prediction is that for the causal problems, we shouldn't be able to do it. And we have a number. We looked at several such papers, a book, a paper for classification, and a paper for regression. And to cut the long story short, it works reasonably well in all cases. So this one is not so clear because it had only one causal data set. This had several causal data sets, and here the message is, so this is the baseline 0. It's always a comparison of a standard algorithm to its semi-supervised modification, a particular kind of semi-supervised modification. And here it turns out that depending which algorithm you use, for the causal data sets, you typically don't get improvements by employing semi-supervised learning. You actually sometimes get even the opposite effect. Whereas for the anti-causal or confounded data sets, you do sometimes get quite significant improvements by doing semi-supervised learning. And yes, question? So how do we define whether it's confounded? It's just by looking at the description of the data set and trying to come up with something reasonable. So we just try to do this before analyzing the data. So we might be wrong in many cases, and the information is all on the web, how we decided which data set we put into where, but one can argue about each of these cases. Yes. And then same story for regression. There's a method called co-regularization, which is some kind of semi-supervised regression. It does help. It tends to help for the anti-causal problems. It tends to not help for the causal problems. So in the interest of time, I will skip this thing here. And so the high dimensional thing you removed. Yeah. So now Dominik will take over again, and I think it's good that we have some time left because this is really quite fascinating. It's in a sense about a theory of graphical models or causal functional models that's independent of statistics and building on other information measures, just to illustrate that this is really about information and we don't necessarily have to use Shannon information.
So after talking about statistics for hours, you should now forget everything what we were talking about statistics, because if you really think how you do causal inference in real life, then you would usually not do statistics. You observe, for instance, these two shortlets and see, well, the pattern is quite the same. So you will infer that there is some causal reason for this similarity. And it's easy to find a reason. They come from the same factory. And so what you do is you just observe that there is a sufficiently complex pattern that occurs here that also occurs here. So due to this coincidence, it's quite likely that there is a common cause behind it. On the other hand, if you look at these two patterns of these two T-shirts, then you would say, well, they are similar in a sense, but not in a sense that is sufficient for concluding that there is a causal relation, because the pattern is so obvious, so straightforward, that you could easily think that every company could come up with it independently. This example is supposed to show that in order to infer a causal relation from similarities, you need some sufficiently complex similarities. So it's not just how much they are similar, or your intuitive notion of how much they are similar depends on how complex the pattern would be. And in order to do mathematics from this, okay, well, I should first explain this slide. We had the causal Markov condition for the statistical case that was basically stating that every observable is statistically independent of its non-descendants given its parents. We could also reformulate it slightly by saying, given all direct causes of an observable, its non-effects provide no additional information on it. And then we slightly change it and drop the statistical and formulate a different kind of Markov condition, the algorithmic causal Markov condition. Given all direct causes of an object, its non-effects provide no additional algorithmic information on it. And to define algorithmic information, I should introduce Kolmogorov complexity. It's originally phrased for binary strings. So the Kolmogorov complexity of a string x is the length of the shortest program with output x on a universal Turing machine. And the interpretation is it's just the number of bits required to describe the rule that generates x. And in the following, I will always have some equations whose equality sign should be taken with a grain of salt, because it's only equality up to some string-independent additive constant. And it's quite common to denote that by this, but in order to keep the notation short, we dropped the plus. And it's important to say that the Kolmogorov complexity is uncomputable. This is why some people think that it's of no practical use, but we still think that it is of practical use. Not only from the philosophical point of view, but I will describe that later. And what's interesting about Kolmogorov complexity is that it's a probability-free definition of information content. So it measures the information of an object, even if it's just a single object. And that's what we need, because that's what we need in order to quantify whether two objects are sufficiently similar to infer a causal relation. But first I should introduce conditional Kolmogorov complexity. K of y given x star is the length of the shortest program that generates y from the shortest description of the input x. And for simplicity, we drop the star. It's the number of bits required for describing y if the shortest description of x is given. And that's a slight subtlety with Kolmogorov complexity, that x can be generated from its shortest description, but not vice versa, because there's no algorithmic way to find the shortest compression that can be proven. That's also the reason why it's uncomputable. Okay, the most important notion now will be the algorithmic mutual information between two strings. It's the complexity of x plus the complexity of y minus the joint complexity. And surprisingly, this can be rewritten as complexity of x minus complexity of x given y, actually y star. And this is the same as complexity of y minus complexity of y given X star. And in the statistical setting, this symmetry of mutual information, like whether you take this term or this term. For Shannon entropy, that's very easy to prove. For algorithmic information, it's quite difficult. So I've seen the proof, but I never went through it. It's really a very deep proof. Okay, and the interpretation is that this expression is just the number of bits that you save when you compress X and Y jointly rather than compressing them independently. Thanks. And algorithmic independence means that this is vanishing. We will also need conditional algorithmic mutual information. That's another, it's pretty much the same. And for our causal inference, we need conditional algorithmic independence defined via this mutual information. That's just a visualization. So this information and this information have this one in common. And then we postulate the local algorithmic Markov condition. Let x1 to xn be observations, so observations in nature formalized as strings. Given its direct causes, every xj is conditionally algorithmically independent of its non-effects. So the same as in the statistical case. And then we were able to prove that we have 3 equivalent Markov conditions in analogy to the statistical case. The recursion formula is slightly different because you have here a sum instead of products, because basically if you replace k with the logarithm of a probability, then you get the same. And this is not a coincidence. There is basically a probability measure that is defined, whose logarithm is defined by the Kolmogorov complexity. It's called Solomonov's prior. And Solomonov's claimed that it's very interesting as prior for any kind of inference problems. And that's related to our approach. Okay, but we have stated this Markov condition and showed that these 3 Markov conditions coincide. But of course, the thing that needs to be argued for is that this is a reasonable postulate that connects algorithmic dependencies with the real world. And that's what we want to argue about now. We recall how the statistical causal Markov condition can be justified, or how Pearl justified it. Pearl justified it via structural equation models, and we just tried to copy that. And the algorithmic excuse me, the algorithmic analogon of a structural equation model is just the following. You have an algorithmic model of causality where you have, for every node, every string is computed from its parents and an unobserved string that describes the mechanism. So this unobserved string is the analog of the unobserved noise term in the statistical sense. And then if we assume that all these unobserved strings are jointly algorithmically independent, then we can show that this implies the algorithmic Markov condition. And so far we have just copied the graphical model framework of the statistical setting. The question is, is it just a straightforward extension? And I think this is one point that is much more than the straightforward extension, because one can show that this framework has implications for the statistical setting. The rough idea, I can't tell about any details here, but the rough idea is that statistical data not only contains statistical information, but also algorithmic information, because if you describe the probability measure, then there's also information content in the probability measure, which is not covered by Shannon information. So the complexity of describing the probability measure is something that is interesting for causal inference as well. And we claim that the independence, the vague notion of independence, Bernhard was talking about that the distribution of the cause and the distribution of the effect given the cause are independent in a sense, and that this could be formalized via algorithmic independence. So we postulated that in the causal factorization of a statistical graphical model, the conditionals P of xj given its parents are algorithmically independent. And in the special case of x causes y, we postulate that P of x and P of y given x are algorithmically independent. And we have used this postulate as a justification of the additive noise models. Okay, I should 5 minutes, right? Okay, but as I told you, Kolmogorov complexity is uncomputable, and so we could either complain about that, or we could just try to approximate it by real compression length. But there's also a different point of view. If we consider the compression length of some data set and worry about whether this is a good approximation for Kolmogorov complexity or not, we could also think maybe the compression length is a nice information measure in its own right, rather than just being a bad approximation for something that is uncomputable. But here's the philosophical question. If we have two files and we observe they can be, if I compress them jointly, then I save a lot of space compared to compressing them independently. Then this seems to show a relation, but the question is whether this really shows a causal relation. And we have argued that it can show a causal relation provided that our causal mechanisms are restricted to a certain class of mechanisms. And we try to invent a kind of graphical model framework for general notions of information measures. So we just looked at the abstract problem. We have n objects, and an information measure is just a function from its power set to the positive numbers. And then we postulate that a reasonable information measure is submodular. The main justification is that if this is the case, then we have a reasonable notion of conditional mutual information via this expression. And this expression is basically copied from the Shannon information expression. So you can rewrite Shannon conditional mutual information as this sum and difference. And submodularity of this function ensures that this is non-negative. The submodularity talk is tomorrow, right? Okay. Okay, so since this is a reasonable measure of conditional independence, we can just postulate the causal Markov condition with respect to this information measure. And we have also 3 equivalent causal Markov conditions, but we have to focus again on the justification, because why should we postulate that this is the case in nature? And there is again the same idea as before. We tried to copy the Pearl's idea with the functional model. So we describe what would be a functional model for a generalized information measure. If you recall the statistical case, in the statistical case we have the statement that the variable is deterministically computed from its parents and the noise. And in order to copy this fact, we just stated this equality, saying that the information of xj, its parents and the noise, is the same as the information of the parents and the noise, because it just says that the variable xj does not add any information compared to the information that is already contained in the parents and the noise. And then we could show that if we assume that and also the joint independence of these noise objects, then we have again a causal Markov condition. Okay, and what's the implication of this theorem? The implication is that if we restrict the attention to causal mechanisms that fit into this framework, so in a way we restrict the attention to mechanisms that fit to our specific information measure, then we can state the causal Markov condition with respect to that information measure. Yeah, okay, 0 minutes. So we have a generalized PC for that one. Maybe just the summary. Conventional causal inference algorithms use conditional statistical dependencies. More recent approaches also use other properties of the joint distribution. And that's the last one, that non-statistical dependencies also tell us something about causal directions. Yeah, this is just selection within Markov equivalence classes just to compare the different approaches. This is our team. Thanks for your attention.
Right. Questions?
Yeah.
Algorithmic causality seems very straightforward, also, and evidence seems very straightforward to the statistical causality. So I'm not completely sure. Can you elaborate on where do you see the advantages of it? I mean,
Yeah.
advantages for me as a computer scientist because I'm very used to it. But what else? What do you learn?
Yeah, you mean practical advantages or?
How does the viewpoint? I don't know. How does the viewpoint? What does it give you as new insights?
Okay, so the question was the new insights from the generalizing graphical models to algorithmic information. That was basically the one slide that I was briefly sketching, that the probability distribution also contains algorithmic information that tells you something about causality. So focusing only on the statistical dependencies loses information, wastes information about causality. We have constructed several examples. Maybe I can show you the examples later. It would require some time, where you can really infer the causal direction just from complexity statements on the distribution.